second lecture on jet substructure. The same notes that were posted out in the hallway from last time still apply here. And I'm going to be covering two topics, that of boosted objects and that of jet grooming. So what we did last time is we saw kind of a first example of a jet substructure where we could essentially go through an analysis from top to bottom where we could see all the moving parts. And regardless of maybe you got lost or confused about the specific derivation that I did, hopefully you got a chance to see what the general strategy was for a jet substructure study. That for whatever you do in jet substructure, you need to figure out what kind of goal you are hoping to achieve. In the case of last time, we wanted to discriminate quarks versus gluons. And you have to identify what physics you think is going to obtain that. In the goofy, strict, soft, and collinear limit that we were doing last time, it was the color factor CF versus CA, which was the physics that we were using. And then the key step, which I don't know a way to automate, so this requires some degree of, if you'd like, model building or creativity, is to construct an observable that's sensitive to that physics that you want. And in the case of quark versus gluon discrimination, there's a really nice paper by Galicchio and Swartz going through a whole tower of different variables that one could use for quark-gluon discrimination. And the one I just happened to use last time was this energy-energy correlation function, where we had this angular exponent beta, where, I don't know if I can tell you exactly why this thing, a priori, why this observable happens to work for quark-gluon discrimination, but somehow there's some intuitive idea that, at least we saw in the Q&A yesterday, that when beta equals 2, this thing corresponded to the mass squared over the energy squared, and that there's some intuitive idea that when you have a gluon jet, there's more radiation, it should have more mass, and so one should be able to use the mass over energy, that dimensionless ratio, to get some handle on quark versus gluons, and then you just generalize that to have an arbitrary angular exponent to see whether you might be able to improve things, and to our disappointment last time, you didn't benefit from changing that value of beta. Though if you include higher order effects, just as an aside, actually beta of around 0.1 or 0.2, this actually helps a little bit. You get a couple of extra percentage points of quark efficiency compared to gluon rejection when you go to higher orders. So once you've constructed the observable, you need to calculate the discrimination. And last time, we were actually able to go through the whole process. We chose a particular expansion, the soft collinear limit. We were able to calculate the discrimination analytically. In general, you don't have that ability, or at least the jet substructure community has not developed the techniques necessary to calculate discrimination for arbitrary observables. We're working on it. And so this lecture is going to be more goofy in the sense of I can only give you heuristics for what the discrimination should be, but instead of calculating the discrimination, you'll just have to trust me that we've run Monte Carlo simulations to figure out what our expected discrimination is. But ultimately, any technique that you encounter, you want to validate in data, find a way of verifying its performance. And for both of these things of boosted objects and jet grooming, I'll briefly mention how these things are being validated in data. Now, what's different between last time and this time? Well, last time we were talking about quark versus gluons, and these jets are fundamentally, intrinsically, one parton-like. That is, we started off with a hard quark, or started off with a hard gluon, that then got dressed up with all this radiation. Some of it which was soft, which was annoying, and then some of it which was collinear that gave you this collimated spray of particles that formed the jet. But it was fundamentally one prong-like. There was a hard single object, gluon versus quark, but a hard single object that defined the observable. And this subscript 1 here was because I was talking about a one prong-like observable. Despite the fact that it's an energy-energy correlation function, the product of energies, we saw that what it really measured was that it measured how much radiation I had coming off the quark versus coming off the gluon. So last time we were doing one prong-like observables. And what we're going to do this time is talk about cases where jets do not fundamentally have one prong, where they're fundamentally multi-prong jets. And we're going to I mean, we can, I'll treat them all at the same time, but just to give you an example of the specific things that I want to think about. For example, W, Z's, and Higgses, W can decay to 2 partons, Z can decay to 2 partons, Higgs can decay to 2 partons, most famously B and B bar. So these objects, if I were to make them, and if they were to somehow form a jet, then these things would be fundamentally 2-prong objects. And in particular, if you wanted to study properties of this type of object, an energy-energy correlation function that C1 would not be a good idea. It wouldn't be sensitive to the 2-prongy nature of these type of jets. I haven't convinced you that they form jets, but I will in a moment. Similarly, if you talk about the top quark decays to BW. The W gives you 2 jets. So this intrinsically is a 3-prong object. That is, if I had a jet that was formed out of a top quark, it intrinsically at the parton level wants to have 3 jets. And then you can imagine beyond the standard model scenarios. If someone says, hey, I have an R parity violating gluino, you say, oh, great, I have an R parity violating gluino. It can decay to 3 jets. If I made one of these guys and if it were reconstructed into a single jet, then it would be fundamentally 3-prongy. And so what we want to do for this is we want to figure out our goal. Our goal is to identify these 2-prong and 3-prong objects. The physics that's governing them, in some sense, it looks really simple. Look, there's just intrinsically, if you actually stared at an event, you would see this has 2 prongs, this has 3 prongs, quarks and gluons have 1 prong. And the hard part is constructing an observable that's actually sensitive to that physics. And then, as I said already, I don't have analytic tools, but we'll be able to get some heuristic understanding of these jet substructure techniques. Okay, so what's the key point? Why do these objects look like jets? And the key point is that if you have extreme kinematics, then these objects, a W, a Z, a Higgs, a top, these can look like one jet. That is, if you use standard jet reconstruction techniques, you would reconstruct these objects erroneously, if you'd like, as a single jet. And let's understand just the basic kinematics that give rise to the fact that these things would look like one jet. So let's take the example of a Higgs, and the Higgs decays to BB bar. And if I made the Higgs in the rest frame in a lab, then the B and the B bar would go back to back. But in general, the Higgs will have some non-trivial transverse momentum with respect to the beamline or just some non-trivial energy. And it is possible to be in a situation where the bottom and the bottom bar are reconstructed into a jet of a radius r. In particular, if you just calculate what the mass of the Higgs is, roughly speaking, the mass of the Higgs squared is the PT of the B, the PT of the bottom bar, and then the delta R separation between the B and the B bar. And roughly speaking, if I'm in a regime where, let's say, these PTs are large, then the PT of the whole Higgs system is just the sum of the PTs of the B and the B bar. And so if I'm in a situation where the PT of the Higgs is large compared to the mass of the Higgs divided by the radius that I'm using to reconstruct my jet, I'll be in a situation where I can get a Higgs mass for where both of the B's are within the same cone, and that can happen if the PT of the whole Higgs system is large enough. And this factor of 2 comes just by treating carefully, well, not carefully, by just assuming that the B and the B bar carry roughly half the energy, plug this into this, solve for the condition that they're in the same jet, and you get this relationship. So in this case, a boosted Higgs, and let's talk about how boosted. So let's say I have a jet radius that's 1, which is a rather large jet compared to, let's say, the 0.4, 0.5, 0.6 that you might be familiar with. But if this guy is 1, Higgs mass is 125 GeV. 2 times that is 250 GeV. But if you're in a situation where the PT of the Higgs is around 250 GeV, that's boosted enough if you have a big enough jet radius. This boosted Higgs looks like a single jet. And because the boosted Higgs looks like a single jet, standard jet reconstruction methods will fail to discriminate this Higgs, which is an interesting object, from uninteresting jets like quark and gluon jets that have nothing to do with electroweak symmetry breaking. Now, you can have two objections to what I just wrote here. So the first objection is you say, come on, why do I care about the boosted regime? Thank you for telling me about the boosted pathology where you go to high energies and things get reconstructed as a single jet. But hey, you know, I'm just going to use small jet radius. That is, I can push up the scale at which this merging happens by making the radius of the jet smaller. If I take a radius of a jet that's half the size, then I need to go to twice the energy before I encounter this pathology. And indeed, one can try to do that. One can try to, instead of using these jet substructure techniques, just use jets that have smaller and smaller radii, and then you can avoid this pathology. The reason why that's not necessarily a good idea is related to something that we saw last time, where we saw these large logarithms appearing in calculations in the soft collinear limit. And those large logarithms, if you start making the radius really, 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 really small, you start to get hit over the head with logarithms of that jet radius. And if the jet radius is really small, then you've actually lost control of your perturbative series, and you just don't know what you're doing. So you can't take the jet radius arbitrarily small. But it is the case that, at least at moderate energies, you could try to do the whole jet substructure business just by using small radius jets. And there are people who work on that and think about how to exploit small radius jets for things like Higgs to BB bar. So that's one thing that you could say, and I can tell you just from experience, you actually do a better job by having big jets that you then find the substructure of than artificially making your jet algorithms have really, really small cone sizes. But that's just experience, and anyway, both things should be explored. But let's say you do accept that we're going to work in this boosted regime and we're going to allow for reasonable radius jets. The complaint that you should have is that, come on, why should I be worrying about a Higgs looking like a quark or a gluon jet? You know, you see that in the boosted regime, a Higgs is reconstructed as a single object, but that's not going to look at all like a quark and gluon jet because, you know, you would say, but a Higgs jet has a mass of 126 GeV. After all, that's the invariant mass of the Higgs, and if the B and B bar are reconstructed into that single jet, Higgs jet has a mass of 126 GeV. While, I mean, come on, quarks and gluons are massless. So, I mean, shouldn't I just be able to measure the invariant mass of the jet? And if I get 0, then I know it's a quark or gluon. And if I get 126, then I know it's a Higgs jet. I mean, so shouldn't I just be able to use invariant mass as like a perfect discriminant? But while it's true that quarks and gluons themselves as partons are massless, the jets that they form are definitely not massless. So this thing is wrong. That quark or gluon jets have plenty of invariant mass. Why? Because I have a quark that's going along. It's radiating off gluons, some of which are captured into a cone of radius r. And these gluons have invariant mass with respect to the quark. Only in the extreme soft and collinear limit is the invariant mass of this guy 0. In general, if I have any sort of angle between the quark and the gluon, I have two massless partons, but they have an angle between them, and if they have energy, I am going to get mass. And a key exercise that I encourage you to do, which you have all the ingredients to do based on the lecture last time, and using the fact that the C1 with a beta value of 2 is m squared over e squared. You can show that for a quark or gluon jet, the expectation value for the invariant mass squared of the jet, that expectation value, it depends on whether you're a quark or a gluon jet, but it's alpha s times CF or CA, depending on its quark or gluon, over pi, times the PT of the jet squared times the radius of the jet that you're reconstructing squared. That is, depending on the jet radius that you use and depending on the PT of the jet, the invariant mass squared of the jet is just not 0. It's proportional to alpha s, so if I turned off radiation, it would go to 0. It depends on the color factor, but it's just not 0. This to be contrasted with the fact that the m Higgs squared is, roughly speaking, a half of the PT jet squared, the distance between the b and the b bars squared. And we see that, for when you get to sufficiently high energies, well, basically the PT squareds drop off, and what you end up having is you have a distribution where, the QCD jet definitely has a chance of faking 126 GeV of mass, despite the fact that you started off with intrinsically massless quarks or gluons. So you need some observable to distinguish these cases. Invariant mass by itself is not enough in this boosted regime, and you need something new. So first, let's just emphasize, so that I did was an expectation value of the mass of the jet. But there is a discrimination variable which is jet mass in the following sense. So if I were to plot the distribution of the mass of my jet, and I had my Higgs, of course my Higgs, up to resolution effects would be at 126 GeV. So if I were to reconstruct my Higgs to BB bar, it would show up as some peak here. Whereas for a quark or a gluon jet, its average value can be large, but the actual distribution is some distribution like this, which indeed you can calculate if you just used the results from last time and calculated the distribution for this C1. And so if you make a cut and isolate events that have where the jet has a mass of 126 GeV, you are able to reject some of the quark and gluon backgrounds. Sometimes the quark and gluon jets have small mass and they just don't fake 126 GeV, or they have too large a mass and they can't fake a Higgs. So jet mass is the first discriminating variable that you should use, but you still then want to separate within events that have the same invariant mass. You want to actually find a way of discriminating between signal and background. So this is certainly a key observable. But we need more. And we have a chance to do more. We have a chance to do more because the quark and gluons are fundamentally one-prong-like jets. The Higgs are kind of fundamentally two-prong. And so it should be possible to develop an observable that's sensitive to the pronginess nature of a jet. Yeah?
If all of the radiation in your quark or gluon jet happens to make it into the jet radius, then the invariant mass of the jet would be 0 because you're just conserving momentum the whole time?
Be careful. By energy momentum conservation, if I have a series of massless objects and I calculate their invariant mass is positive. And the reason why I escape your complaint about energy momentum conservation is that if I think about this as a Feynman diagram, so I have an actual Feynman diagram with gluons coming off. This guy is off shell. And this guy has an off-shellness, and if you're right, if I were to capture all the radiation coming from this guy, then what I would measure its off-shellness, but it's not on shell, it's off shell. And you can see that at the level of the Feynman diagram, that if you're not in the extreme soft and collinear, this is just not an on-shell particle. So there's no sense in which quark or gluon jets are massless. In fact, because of Sudakov suppression, the probability for it to be exactly massless is 0. Quark and gluons manifested in an experiment have mass. And there's no way avoiding it. And any analysis that says, oh, I see a jet and I assume that it's massless, well, it may be an okay thing to do. It may be a small modification, but strictly speaking, it has mass. Okay, other questions before I start talking now about specific variables that are able to test the pronginess nature of jets. So we figured out our goal. Our goal is to test for pronginess of jets. Now we need to figure out the physics, and we need to figure out what physics can I use to actually probe that pronginess. And one of the exciting things about the jet substructure community is that different people have different intuitions about what the leading effects are and what the dominant physics that one should use to probe those effects. And so there's actually been a number of different pictures for thinking about how one tests for pronginess, coming from, in some sense, in what order in perturbation theory does your mind naturally work in? And depending on what order in perturbation theory you have the intuition, you actually will propose different observables. And in some sense, the best observable that one could write down is one that benefits from all those different types of intuition. So the first type of intuition would come from what I would call leading order structure. So we have two things that we're trying to discriminate between. We're trying to discriminate between a Higgs to BB bar. And we're trying to tell that between, you know, with the special case of the Higgs, you can actually use B-tagging information to help further discrimination. But let me ignore the fact that these actually are B-taggable for the moment and just talk about generic quarks and gluons. Just as an aside, for Higgs to BB bar, the thing that actually you should be worried a lot about is gluons splitting to BB bar, because these also have two B tags, and you would need to find ways, strictly speaking, to tell a gluon splitting to BB bar from a Higgs going to BB bar. But let me ignore that for a moment and just say I'm trying to tell Higgs apart from quark and gluon jets. So I have a quark. And I want to tell the difference between these two objects. And so why do I call it leading order structure? Leading order because this is the first order in perturbation theory, where I get mass, Higgs going to BB bar, obviously it has mass. And if I want a quark to have mass, it better have at least one emission. And so this one emission says that at order alpha s I get a mass, and so this is leading order structure. The first structure, the first order in which I have a chance of having a jet that could fake a Higgs. And if you stare at this leading order structure, you would say, okay, what can I use to tell at the leading order level between these two objects? So in the case of a Higgs going to BB bar, there is no soft collinear singularity, just Higgs going to BB bar. In its rest frame, the B and the B bar have the same energy. And in a boosted frame, they roughly have democratic energy sharing. And more particularly, you can go through an exercise to convince yourself that if I look at the energy fraction, so this is the, let's say, the energy of the B compared to the energy of the Higgs itself, that energy fraction, that if I look at this distribution, that this guy is flat. That is, all values of z end up appearing equally well when I'm at sufficiently high boost. So I have democratic energy sharing. And so on average, the B carries half the energy and the B bar carries half the energy. In contrast, for the quark splitting to a quark and a gluon, here I fixed the invariant mass, but I still have information about the singular structure of QCD. So here, despite the fact that I've got an invariant mass, I still have the soft singularity. And we saw last time that the distribution I get because of the soft singularity goes like 1 over z. That is, for a given mass, how does a quark or gluon jet want to get that mass? It wants to get that mass from having the smallest z value it can possibly get away with. So I want small values of z. But then to have mass, I better have large values of the angle. If I want to have the way that QCD wants to generate mass, it says I want to have soft splittings, and then they have to be at wide angle. And so the first thing that you would do if you want to talk about quark versus gluon discrimination is that you'd want some variable, some observable, that could measure the energy sharing. And that's the thing that you would want to do at leading order. So leading order observables, they're going to somehow use this energy sharing. And you can convince yourself that all other things that you could try to do are essentially the same as energy sharing. There just aren't that many kinematic variables that you could use if you're only going to leading order. So I'll give you an example of a variable that, that tests this leading order structure. In fact, the original jet substructure technique, which is the BDRS method. And the BDRS method explicitly does a test for the energy sharing. So if you're thinking at lowest order in alpha S, that's the picture that you might have for a jet. Now, if you're thinking at one higher order in alpha S, you might have a different picture for how to test for the pronginess nature of a jet. So I'll call this subleading structure. And let's see what jets look like at one higher order in alpha S. So if I have a Higgs going to BB bar, at one higher order in alpha S, I would generate additional radiation. And where can that radiation come from? Well, the Higgs is a color singlet, so it's not coming from there. So the radiation would have to come off of one of the B's. Okay? And then we want to compare that to a quark splitting to a quark and a gluon. So this was the leading order structure. And then what's the subleading structure? Well, the subleading structure is I can have radiation coming from any of these objects. All of these carry color, so I could have radiation coming from this, from this, from this. And somehow you want to distinguish these two cases. So one thing that's going to be helpful is the fact that the Higgs is a color singlet. And because the Higgs is a color singlet, this gluonic radiation, basically I can figure out the pattern of gluonic radiation in the Higgs rest frame. So I have a Higgs, it has a BB bar, it has gluonic radiation going all around in its rest frame. But then that whole system gets boosted. All that gluonic radiation collapses down, and basically this extra subleading radiation is confined to within the BB bar dipole, if you'd like. And I don't have gluons at large angle relative to the Higgs. So because of the color singlet nature, radiation is confined to the BB bar system, and I don't have wide angle radiation coming off this color singlet object. In contrast, this quark is color connected to the rest of the event. What conserves color is this quark is connected to other quarks or gluons elsewhere in the event. And so this radiation, because I'm now color charged, the radiation pattern is much more complicated. In particular, I have soft radiation everywhere. And this gluonic radiation coming off the quark could be pointing in any which way direction because there's no color singlet anywhere in the jet that I'm trying to probe. We can now try to use this information in order to build a substructure observable. And there's many different substructure observables that I'll talk about, but I'll just mention one from my own work, which is called N-sub-jettiness. Then there's a whole other list of techniques that are trying to even more accurately pull out information about the color structure of the jets that you're producing. And so I'll show that particular example. But more generally, if you're trying to test for the pronginess nature of a jet, the kind of ideas, the generic ideas that have come about by looking at this leading order and subleading structure is that you want some kind of observable, construct some kind of observable that accomplishes one of the following tasks. And it would be great if someone in this audience could come up with another strategy, but here are the ones that exist in the literature. One is that you want to toss out soft wide-angle radiation. For the case of a quark, either at subleading level or at leading level, the mass is coming from soft radiation. We see that explicitly because of the soft singularity. And so this large amount of mass that I can get from a quark or gluon jet is coming in part because there's all this soft radiation going around. And if you can find a way to toss out soft wide-angle radiation, the wide angle is because that's the thing that gives you the mass of the jet. If you can toss this out, then you'll find a way to better reconstruct the jet that you're trying to study and better separate Higgs from quark or gluon. The other thing that you could try to do, based on what we said, is you can try to measure Z and come up with an observable that measures Z. Now, Z by itself is only defined at lowest order in perturbation theory, so you need to have some thing that works at all orders in perturbation theory to measure z, but you want to find some way to measure z. That's one option. Another way is to directly test for n prongs. This is what n sub jettiness tries to do, and what it's doing is it's saying that the radiation pattern is going to be collinear to the hard partons in the event, and so you want to test for that, whereas here the radiation pattern is more diffuse, and I'll show you that explicitly. And then finally, people have thought about testing directly singlet versus non-singlet by explicitly making use of the soft radiation pattern and trying to guess what the underlying color structure of the jet that you've produced are. And as I said already, there's algorithms, there's observables that try to do all these various methods. In some sense, the best thing you can do is try to do everything at the same time. And I apologize to, I guess, is there anyone in the audience who's worked on things that are not one of these two things? Well, apologies to you. Given finite time, I want to just highlight these two examples, partly because they just demonstrate the dominant types of possibilities for what the physics could look like. Okay, so let's start with the BDRS method. Butterworth, Davison, Rubin, and Salam came out in 2008, and I think this paper can lay claim to starting the entire industry of jet substructure. Certainly, this paper, along with the anti-KT paper, really changed my idea about what you could do with jets. There's one caveat. These guys started the jet substructure industry in the sense that they have the most citations for doing jet substructure. But there's actually some previous work that Mike Seymour had done in the 1990s that actually anticipated a lot of the effects that showed up only 15 years later. Anyway, these guys get a lot of credit for really pushing on jet substructure. And they were particularly interested in the case of associated Higgs production, where you make the Higgs in association with a Z, a Higgs goes to BB bar, and they showed that using substructure techniques, pushing into the boosted regime, you could actually make it possible to see the Higgs to BB bar decay channel. Okay, but we're going to just think about this BDRS method a little bit more generally and figure out, okay, how are they able to, in particular, measure Z, which is the leading order structure that BDRS is trying to be sensitive to. Okay, so this procedure that I'm going to show you is a procedure. It's an algorithm. And so I want to define the algorithm for you. It's not an observable in the sense of, I hand you a collection of 4 vectors and you can instantly write down a closed form expression for what these variables are. It's an algorithm that you apply to a set of 4 vectors and then you do various tests to see whether you do or do not continue down in an analysis chain. So the first step of BDRS is to recursively cluster a jet. And you recursively cluster a jet with something that's known as the Cambridge-Aachen algorithm, but more easily just say recursively cluster a jet with nearest neighbor. Nearest neighbor recombination. So what do I have? I have a collection of particles in my jet. So I have my jet here. I have a bunch of different particles contributing to my jet. And what this recursive procedure does is, in some sense, the simplest way of putting a jet back together. Take 2 particles in the jet, or in particular, take the 2 closest particles in the jet, find them. So in this case, I guess these 2 are the closest. You find these guys, and you combine them into a single 4 vector. So you take 2 4 vectors, take the collection of 4 vectors, take the 2 that are closest together, put them back together, and now go to the next stage. Okay, the next stage is you take, I guess these 2 are the closest together. So you put those together into a 4 vector. I guess these 2 are now the closest. You put those together into a 4 vector. And then finally, at the last stage of the clustering, you put these 2 together to get your final jet. You can actually apply this procedure to entire events, but you're just doing nearest neighbor in angle. Yeah?
The original jet was clustered.
What?
The original jet was clustered.
Good. So in the original BDRS paper, the actual jets were found using the same recursive algorithm. But more generally, I mean, you can imagine any technique for finding the overall jet, and then whatever technique you find the overall jet with, you can then apply this procedure to that. the original procedure uses the same procedure to find the jets in the first place, but that's not strictly speaking necessary. So imagine that this was clustered at anti-KT, and then I do this recursive clustering procedure on the jet that I already found. Again, this is this apology that I made last time that I'm not really talking about jet algorithms themselves. Okay, so once you've done this recursive clustering, now you want to unwind the jet. So you've clustered everything into a tree, and now you want to unwind it. And the way you want to unwind it in a way that is sensitive to energy sharing. And the beautiful thing about this pairwise recombination is that at each stage of the clustering, there's a well-defined notion of Z. So I have the overall energy of the jet to begin with, and then this energy of this jet is shared between E1 and E2, and as long as your recombination conserves energy momentum, E jet is going to be E1, it will be E1 plus E2. And without loss of generality, I can just say that E2 is going to be smaller than E1. And you unwind the jet by applying the following test. So you require that when you unwind, if you want to keep the unwinding, you require that E2 over E1 is greater than what's known as Y cut. So let's say E2 is smaller than E1, so this thing, roughly speaking, you can think about this as being the same thing as Z, where Z being small means that you're soft. And if you're what this requirement of the unwinding is saying, I only keep things if I'm hard. Above some Y cut value, let's say this thing is of order 0.1, only if the two guys are democratically sharing energy with one guy carrying at least, let's say, 10% of the energy of the whole system, only in that case do I keep that unwinding. And then this procedure also has another criteria, which is that, and this one I'll have to wait to explain. So this is one criteria, and the other criteria is that the maximum of the mass of one guy versus the other guy over the mass of the entire jet, that this guy is less than mu cut. So I'll come back to this guy in a second. So I unwind and I apply those tests. If the test fails, that is, I didn't have a democratic energy sharing, and I didn't satisfy this mu cut thing, which I'll mention in a moment. If I failed this democratic energy sharing, then that does not look like a Higgs. It looks more like a quark or gluon jet. So if it fails, then throw out the softer subjet. That is, throw off the soft piece, eliminate it, and then continue recursion on the harder guy. So what is this doing? This is saying I did a splitting. It doesn't look democratic. This looks more like a quark or gluon jet, but I'll give you another shot. I'll throw out that soft guy and see whether the remainder piece might still have a chance of having democratic energy sharing. And if the test succeeds, in that case, you found your jet. So if you do this recursive clustering and you find that the last stage in the clustering had democratic energy sharing, you automatically pass the success. You found something that really looks like a Higgs. But otherwise, you toss out soft radiation until you find something that looks like a Higgs. And for quark or gluon jets, if you apply this procedure recursively, what you find is you just toss out all the soft radiation, and then you end up pushing your mass distribution way, 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 way down, and you no longer look like a Higgs anymore. And so then you wouldn't satisfy the mass criteria here. So this was the original jet substructure algorithm, and you see it's doing a lot of different things. First, it's doing this recursive clustering. Why? It's doing it so I can define an energy sharing. So we see this energy sharing here. So this is energy sharing. This procedure here is a little bit more interesting. So this thing is called mass drop. And this thing is saying, take your jet, divide it into two pieces, and I want to make sure that most of the mass is coming from the angle between the two objects and not from the objects themselves. So in Higgs to BB bar, at leading order, okay, the B's carry some 5 GeV of invariant mass. The Higgs has 125, and most of the mass of this is coming from the angle between these guys. And I want to make sure that the mass of the individual prongs is relatively small. I want to, in a sense, test for the presence of just hard prongs with no invariant mass, and that's what this mass drop is doing. You want to find a clustering that's not only democratic in energy sharing, but also really resolves into two pieces where the subpieces have less mass than the overall system. Another thing that's happening here is that we're doing this throwing out of radiation. This thing is a type of grooming, which I'll discuss more in the next part of my lecture. But you're tossing out soft radiation, and by tossing out soft radiation, you're also improving your mass resolution. That the Higgs could have been contaminated by soft radiation, you're removing that from the signal, but then the background is being generated mostly by soft radiation, and you're getting rid of that. So a lot of things going on in this algorithm, relatively easy to state on the board, but it kind of incorporates a number of the different features that you might want of a substructure technique. It was originally developed for two-prong things, Higgs to BB bar. You can try to generalize it for three-prong objects, but it somehow has the right physics in it for doing two-prong identification. And I should say it's actively being pursued and used for particularly Higgs to BB bar searches at both ATLAS and CMS. So questions about this observable. So this is an algorithm, a procedure that I use to take a jet, unfold it, unwind it, and then try to get at the core Higgs that might be buried underneath. Okay, so that's one thing using the leading order structure. Now let's talk about a different algorithm, or a different procedure, a different measurable, observable, that is testing the subleading structure. So while I'm racing the board, if questions come up, feel free to interrupt. Okay, so the next type of observable we're going to do is of a different form. It's not an algorithm, it's just an observable. It's something where I hand you a bag of 4 vectors and you hand me back a number. In that sense, it's more similar to what we did last time with the energy correlation function, in that I have a closed form expression for what this object is. And the observable is n sub jettiness. That I developed with one of your classmates, Ken Van Tilburg, in 2010. It was based on some work that my QCD colleagues, Ian Stewart and friends at MIT, were working on. It was a nice crosstalk between they had a QCD reason for wanting to understand a variable that they called n-jettiness, and we inherited the silly name and just added sub to it so that it was relevant for jet substructure. And bizarrely, that this version of it, the substructure version, is more famous than the original n-jettiness, which is a really event-wide version, though both have the same intellectual roots. So this observable is, given its name, it better be sensitive directly to n-prong structure. Come on, n sub jettiness, it better be directly related to n-prong structure. And it better, in some sense, test for the subleading radiation, and I'll explain more about why that's the case. It was first applied for boosted tops. So the first thing that was done to test for 3-prong structure was 3 sub jettiness, but you can apply it for 2-prong, and even surprisingly, 1 sub jettiness is actually a useful observable as well. Okay, so what is this observable? So it's called tau sub n. N tells you the number of prongs. And it has some, it's a dimensionless object, so there's some normalization factor to make it dimensionless, but the specific version of this normalization isn't that important. And what do? You sum over all particles in your jet, and you take their transverse momentum. And then you weight the transverse momentum by the distance to a subjet axis. So I take the distance of that particle to a subjet axis 1, distance to a subjet axis 2, all the way up to the distance to the subjet axis n. And I raise this thing to the beta power if I want to have a generalization, just like we had this beta power in the C1 variable. For this talk, purpose of this talk, I'll try to ignore the beta dependence, and so we'll just talk about things raised to the linear power, which is what we said in the original paper, but you can imagine generalizations. Okay, so this observable, I mean, I can write it down in one line, but there's things buried in this definition. So these things, 1, 2, or 3, 4, up to n, these things correspond to subjet axes. So we have n axes, subjet axes. And each of these we have to find a way to define. So you give me a jet, you find where you think the subjets are lying, and then you calculate what this observable is. And I'll talk about different ways of calculating or picking where these axes go. But the way that this variable is designed is such that it's normalized such that it lies between 0 and 1. And if this thing is large, if this thing is 1, then it's normalized such that the distance to any subjet axis is big. Basically, you have some jet with radiation all over the place. None of them are collimated at all with the subjet directions. And so this tells you that it's not very n-subjet-like. Things are not arranged close to n axes. And so this tells you that you have greater than n subjets. Where in contrast, if this thing is 0, that means that each term is 0, which means that the delta R between that radiation and any individual subjet axis better be 0, which is to say that things are well aligned along n or perhaps fewer subjet axes. So greater or less than or equal to n subjets. So this thing is easier to show if I draw a picture of what's going on. Again, this is just an observable, calculable in QCD. You know, just like this energy correlation function, this is just some thing. You give me a list of 4 vectors, I can just calculate this object. So let's consider, just as an example, a boosted top. And we want to compare a boosted top versus a QCD jet that happens to have an invariant mass close to the top, M jet of order 170 GeV. Okay, so let's think about the boosted top. Top goes to BW, which goes to B jet jet. But I'm in some boosted regime. I'm in a regime where all the top decay products happen to be clustered into the same cone. So I have my jet. But inside my jet, really, fundamentally, it's 3-prongy. There's 3 prongs of energy. And this observable here is supposed to tell me that it's 3-prongy. Okay, so let's see how it works. So first, I need to choose n axes or n subjet directions. So, I don't know, I eyeball this thing and I say, I don't know, put the subjets here. So you can imagine getting a bunch of your friends together, and you're given all the events of the LHC, and you just get to draw X's on each jet to figure out where the subjet axes are. Or you can have some kind of algorithmic procedure that specifies where they go. Or the best thing you can do is just try all possible subjet axes and just take the one set of subjet axes that minimizes the value of n subjettiness, such that you find the axes that are as good as you can lined up along the directions. And indeed, that's what's typically done in an experimental context. You find the subjet axes that minimize n subjettiness itself. In that case, you want these subjet axes to align along the dominant amount of radiation in your jets. So you found these 3 axes, and then you want to calculate that observable. So because of that minimum, what that minimum says is that I want to calculate the distance from any particle in this jet to the closest subjet axis. So this procedure is called Voronoi tessellation. You find nearest neighbor regions, such that if I'm in this pi wedge here, then all the particles here are closest to this subjet axis. Within this wedge, they're all closest to this one. Within this wedge, all closest to this one. And then you calculate the distance of all these various particles to that subjet axis, sum their PT, and you see what number you get. Here, the axes have locked on to the right substructure, and all the radiation is lined well along that substructure, so this thing is going to be close to 0. That is, I've successfully found something that has 3-prong-like structure, and therefore the boosted top should have a small value of this tau 3. Now compare that to what happens in a QCD jet. A QCD jet is fundamentally 1-prong, but somehow it accidentally got large mass because there's lots of soft radiation. So a QCD jet looks like some blob of radiation, maybe some stuff over here. By eye, if you look at enough of these events, they just don't look 3-pronginess. But this observable is undeterred. It will calculate 3-pronginess whether it's 3-prongy or not. So it tries to figure out where are the subjet directions, and it gets really confused. It says, I don't know where they are. I don't see anything. Yeah, maybe it's here, maybe it's here. I don't know, maybe it's here. You again do the tessellation into nearest neighbor regions. You calculate the observable, but I don't know, the subjet axis may or may not be related to anything that has anything to do with physics. And so this tau 3 is ambiguous. That is, who knows what the distribution is going to be for this? There's not an intrinsic 3-subjet-y structure to it, so I don't know, it's going to be some blah distribution. Might be small, might be large, who knows? Okay, so now we need to somehow turn this guy into a machine for identifying 3-prong nature. And here's a way of doing it. So the boosted top is really 3-prong-like, but it's not 2-prong-like. So if I were to do the same thing, if I were to do for 2-subjettiness, I would have these 3 prongs of energy, and I'd try to find 2 prongs to try to calculate 2-subjettiness, and I'd say, here's 1 prong, and then I don't know where to put the other prong. Well, I just put it somewhere in between. Divide the thing into regions, calculate the distance between all the various particles to that region, and we'd find in this case that it's not 2-subjet-like. And in that case, tau 2 is large. Whereas if I go back to this QCD jet, it didn't want to be 3-subjet-like, and it doesn't care about being 2-subjet-like either. It just says, I don't know where the axes are. And this tau 2 is also ambiguous for a QCD jet. But here we now see leverage. We see that for the signal, we have small values of tau 3, large values of tau 2. For QCD jets, it's kind of ambiguous, and where I put the axes doesn't really matter. In fact, tau 2 doesn't really change compared to tau 3. And so you now can use this to make a discriminant variable. You can say, let's make a 2-dimensional distribution of tau 2 versus tau 3. You can show actually that tau 3 is always less than tau 2, so I can never be up here. For top jets have small value of tau 3 and large values of tau 2, so top jets tend to lie along here. Whereas QCD jets are ambiguous, all the numbers are relatively large, and so QCD jets tend to lie up here. And so we see we can discriminate between top jets and QCD jets by having a cut that goes along the diagonal, and in particular, tau 3 over tau 2, the ratio, this thing being small, being less than some cut value. This is a good probe for top jets versus QCD jets. QCD jets are ambiguous with respect to the ratio, or the kind of order 1. Top jets have a hierarchical separation, so in the ratio, this thing is going to be small for top jets. And you can do exactly the same thing that I just did up there for let's say 2-subjet things. If I want to look for Higgs versus QCD, you'd find that QCD jets for tau 2 and tau 1, QCD jets have large values of the ratio, whereas if I really had a Higgs jet, I would lock on to the substructure, and in this case, tau 2 over tau 1 would be a good discriminant. And both of those type of observables can be used for figuring out the subjettiness of an event. So why does this variable work? So let me just bring the variable up one more time. Why does this variable work? Well, if I really had a boosted object, then the mass is coming from hard prongs. And this thing vanishes when I find the subjet axes that lie along those hard prongs. And so for boosted objects, I have a hierarchy that if I have n prongs, then tau n is much, much less than tau n minus 1. And so I can use, if I want to find n prongs, I want to have this guy small compared to this. Whereas QCD jets just have no prong-like structure, and so this tau is ambiguous. And so kind of anything that I do is going to give me some random value. Said another way, QCD just gets their mass from one energetic core. And when you have one energetic core, this variable doesn't really want to be small. Yeah. Oh, so between how sharp is the separation? Right. So let's see. So visually, let's say I take jets that have a mass already around 170 GeV, and I calculate the distribution of tau 3 over tau 2. Visually, what you'll see is something that looks like roughly like this. For this is QCD, this is tops, and so a cut like this, you see kind of roughly what the separation would be. So it's not like awesome separation. I can't like tell everyone apart. But the separation is, if you like to think about it, it's comparable to, perhaps a little bit better than quark-gluon discrimination in terms of the level that you can get. If you combine n subjettiness information and mass information, then roughly speaking, you get a rejection factor of like a few times 10 to the minus 3 of QCD jets against top jets. A lot of that's happening just because of the mass cuts. But you're able to get into a regime where, if you weren't using the mass information, you would say, oh my God, this is better than B-tagging. A few times 10 to the minus 3, fantastic. But a lot of the work is being done for you already by the mass. And then the incremental thing that you get is a little less than an order of magnitude improvement. OK. So both of these methods are being used in data right now. For example, this tau 2 over tau 1 has a kind of cute application. So BDRS was originally designed for Higgs to BB bar, and tau 2 over tau 1, well, we originally thought about tau 3 over tau 2 for top jets. But tau 2 over tau 1 has had kind of a fun application. Sorry, let me just do it over here. So Higgs to BB bar, this BDRS is being used for this. But an application where n subjettiness kind of surprised us that this would be useful is Higgs at 126 decays to BB bar. But let's say you thought that the standard model Higgs were closer to 400 or 500 GeV. So you're doing a search for the standard model Higgs. Of course, we know where it is already, but you want to do your due diligence and test where it is elsewhere. And let's say this Higgs instead were, let's say, 500 GeV. In that case, one of the dominant decay modes of the Higgs is to WW. And these W's can go, let's say, to two jets. Maybe one side goes to lepton and neutrino. But you start off with 500 GeV of energy in a standard model Higgs at 500 GeV. Decays to two W's. Each W has 250 GeV. The mass of the W is only 80, so this thing is actually moderately boosted. And I think it's the CMS experiment is actually using, for this W, you're in a boosted regime, and they're actually using tau 2 over tau 1 to try to test for boosted W's coming from heavy Higgs decays. And this is an interesting discriminant variable and an interesting use of a discriminant variable where, hey, it's just something you can calculate in QCD. Once you have it, you can apply it everywhere. And so it has applications beyond what we had originally anticipated with boosted tops. So let me just make one further comment before going on to the last subject of these lectures, which is about why it's so important to have this intuition about what you're trying to accomplish, or identifying what the important physics is that you're trying to study. So, what was BDRS designed to do? BDRS was designed to test for democratic energy sharing, but it does not test for n prongs. As part of the BDRS procedure, there's no test along there where it says, is radiation well collimated along axes? N subjettiness was designed to test for n prongs, but does not test for Z symmetry, or for the Z democratic energy sharing, Z sharing. And so in some sense, you see a deficiency of each of the methods. You have all this information in principle that you should use, and you could do either a boosted decision tree and try to do both of these things at the same time. That's one strategy. Or you could try to come up with another observable. And so you can try to have this plus this equals some other observable. And I mentioned for you the energy correlation functions, which was C1. Well, now if you add these things together, you get an energy correlation function that's called C2, which you can ask me about tonight if you care about it. But just to say that knowing what the physics you're trying to do is can help you figure out new observables that can leverage all of that information. Okay, so questions before I move on to the last topic, which is that of jet grooming. Yeah.
Just a quick question on what was already asked before about the separation of this.
Yeah.
Observable. Like, can you just, is the separation so good that you can just, in the end, do a simple cut on this plane, or do you have to do like something like neural network on that kind of stuff? How does that?
Right. So always, multivariate techniques always will do better than a simple cut. Okay? But you can ask the question, is a simple cut sufficient enough to get you down to the level where you're starting to test already differences between the training samples? And so it is always true that you can do multivariate cuts and you'll always do better. But the reason why the ratio does best, as far as we can understand, is that it actually has one additional feature that you want of a substructure observable, which is that it is quasi-boost invariant. Other things that you would do, if it were some general function of tau 3 and tau 2, if you boosted to a different frame, the variable would change dramatically. But the ratio, the Lorentz boost in the numerator and the Lorentz boost in the denominator roughly cancel out. It's not exact, so it's quasi-boost invariant, which is why the ratio ends up being the better observable in practice. And in fact, if you run a boosted decision tree where you don't put the ratio in, you get some discrimination power. That is worse in general if you don't have a big enough training sample than what you would get the discrimination power having the ratio. But if you start off with the ratio in there in your boosted decision tree, you definitely benefit from it, including additional information. And part of the things that you can do is you can leverage this angular exponent, which I keep writing down and then erasing, and using different values of the angular exponent to try to tease out more information. But I do not have an analytic calculation of any of this. And so it's not obvious to me whether all the manipulations you do is just playing with Monte Carlo or whether it's real physics. And the jet substructure community is trying to do an actual calculation to validate that these things work the way we think they do. They work fantastically in Monte Carlo, seem to work well in data, but you'd like to have an analytic understanding before you declare victory, and especially before you start doing too many boosted decision tree type or multivariate techniques. Yeah. If you boost this thing along the jet direction, it's quasi-invariant. It's not actually invariant. Sorry, ask that again? If it's not boosted very well, then this thing is definitely not boost invariant. So when No, it doesn't. No, sorry. This technique, or at least as I described it, this technique only works if you have jets that are already collimated within a reasonably small radius. If you try to apply this to tops that are roughly created at rest, then this sum is not just over all the particles in the jet. This sum now needs to be over all the particles in the event. And once you start doing that, you get sensitive to all sorts of crazy beam effects and such. So to the best of my knowledge, though I am actively working on this, to the best of my knowledge, I don't know how to apply this to event-wide. But you'd love to do it. You'd love to be able to say, hey, I want to identify tops in all kinematic regimes. And during Q&A, you can ask me what ideas I have on that front of trying to generalize this variable in a way that you could do it even if you're only moderately boosted or not boosted at all. Yeah?
Could you comment on the usefulness of using these methods for known standard model objects like tops and W's versus looking for new physics?
Right. So new physics objects, these techniques can be applied if the new physics objects themselves are boosted. So if you have some cascade decay, giant cascade decay, generating a lot of energy that the end part of the decay can be boosted, then you can use these techniques in those cases. The challenge is that you don't know ahead of time what the mass is. And so now you need to play a little bit of a different game. It's no longer a question of what's the efficiency if I make a mass cut and a cut on one of these variables. It's the question of what is the efficiency, having made a cut on those variables, to find a bump in the mass. And those are slightly different questions, but you can try to do this. And the Atlas experiment did a test where they were looking for an R parity violating gluino. They didn't know what its mass was ahead of time, but they used tau3 over tau2 to try to isolate a sample that was enriched with boosted RPV gluinos. And that search was moderately successful. That was something where the boost wasn't quite big enough to really benefit from this technique, and you ended up doing a little bit better just by using small cones, that you didn't see the dramatic improvement that you might have wanted to. But if the RPV gluinos were more boosted, that is, they were coming from a cascade decay higher up from I don't know what, then that technique would have worked a little bit better. But there, the gluinos were kind of made roughly at rest. You didn't really get enough of a boost to make a huge impact. But that strategy is being pursued. Okay, so in the last, I guess, 20 minutes, I want to talk about the last topic, which is that of jet grooming. And this is a topic that is going to evolve considerably over the coming years because at the LHC we're going to high luminosity, and the issue of pileup is going to become an enormous concern. And because pileup is an enormous concern, you can legitimately worry whether any of these jet substructure techniques will be robust when you now just start filling all 4 pi with garbage from secondary collisions. And what jet grooming methods try to do is they try to mitigate various sources of contamination that could infect your jet. And you hope that, that by applying a grooming technique, you can get relative insensitivity to pileup, and then you might also get some secondary benefits if you can remove soft contamination. So just to introduce jet grooming, let's come back to the question of what is a jet. So what is a jet? You have a cone of size r, you have all the hadrons going into that jet. And so you say, oh, great, I have a quark going into that jet, the quark radiates off final state gluons, those all into my jet. This is what my jet looks like. And that would be a beautiful picture if it were true. But, you can't just draw a cone that only includes final state radiation. You have to deal with other things that might end up in your cone. So the real collision has protons. The protons, what you're actually extracting out are the quarks and gluons out of the proton. The collision that might have given you a hard quark came from, let's say, a parton collision here that gave you a quark coming off. And from a single collision of partons, I can end up having initial state radiation that just happens to be generated at wide enough angles such that I have ISR, initial state radiation, that ends up in my jet. So despite the fact that I wanted to measure the radiation coming from a final state, quark or gluon or boosted Higgs or boosted top, what I end up getting is contamination from initial state radiation. There's also secondary parton collisions where I can have one of the 2 other partons collide and give me some radiation. This thing is often called underlying event, or at least a component of this is called underlying event. And this is yet another source of contamination. It's radiation uncorrelated with the thing that I want to measure and just spouting garbage into my, into my jet. And then the thing that, in principle, you can control by running your experiment in a different way. These 2 ones are not reducible. They're just there. There's nothing you can do about it. It's just PP collisions. You can't turn off ISR, and you can't turn off secondary parton collisions. The thing in principle you could turn off is you could turn off secondary hadron collisions. That is, in a single bunch crossing, having secondary proton collisions that go up into your jet. So this thing is known as pileup. But if you want to get high statistics, then pileup is just the name of the game, and you just have to find a way of dealing with pileup. A huge issue when we go, well, already a huge issue with 7 and 8 TeV data, but even more as we go to higher luminosity. So why does this matter, this contamination? So jet grooming is trying to attack the problem of jet contamination. And why is this such a big issue? Well, let's say I'm looking for a boosted Higgs, for example, and I look at the mass distribution for a boosted Higgs, and I'm supposed to get a peak like this if I had no contamination. My peak at 126 GeV from my boosted Higgs. But if I have contamination from other parts of the event, I'm adding additional 4 vectors to my jet cone region. And if I don't have some procedure to remove them, then I have 2 different effects that happen. One is that I just add garbage, and I shift the overall mass distribution. So I have an overall shift of the mass distribution when I add extra radiation. Now, if I had an overall shift that was the same for each individual event, you wouldn't care. You could just correct for it. So the overall shift is not the issue. The issue is that on an event-by-event basis, I might get more or less radiation contaminating my event. And so I have a degradation of my mass resolution, because for some events, I only have a small amount of contamination. The mass only shifts by a small amount. Other ones, I have a large amount of contamination. And instead of having a nice narrow peak, I have a broadened distribution. And if I just do an overall shift, I can make it centered at 126 again, but I can't get rid of this degraded mass resolution issue. And so the goal of jet grooming techniques is to try to deal with this degradation of the mass resolution due to these various sources of contamination. And so many techniques have been proposed. They go under the generic name of jet grooming. There's techniques like trimming, filtering, pruning, mass drop. They're all things that are trying to remove contaminating radiation. But let me just mention 2 of them just to give you a sense. So the first one, and I'm going to go through quickly, and you can ask me more this evening if you want more information, but I just want to give you a flavor for these. So one of them is called area subtraction from 2008, came out around the same time as the anti-KT papers. And this thing was specifically designed for pileup. And this method is quite ingenious. Take your event in the eta phi plane. Take your event. You want to find some jets. Here's where the hard cores of radiation are that I want to study. And what pileup does is, actually kind of surprisingly, it generates roughly uniform sprays of radiation in the coordinate system of eta and phi. That is, pileup kind of uniformly contaminates things in this coordinate system, roughly speaking uniformly. You can try to be a little bit more sophisticated by that. But you can think about pileup on an average basis is just giving you a uniform amount of contamination everywhere in your event. And so you have a uniform density of contamination. Let me just call that density rho. Now, on an event-by-event basis, the amount of contamination that I have is different. So sometimes I have large amount of contamination, I shift the mass distributions a lot. Sometimes I have a small amount of contamination, I just change them a little bit. But on an event-by-event basis, while there are fluctuations about where the contamination ends up, roughly speaking, still the contamination is reasonably uniform for any individual event. So on an event-by-event basis, you can make the approximation, the 0th order approximation, that the pileup is uniform in the eta phi plane. And if you can estimate the density of contamination, for example, you can mask out your jets and just measure where the jets aren't, estimate the density of contamination. And then you can correct for the contamination with a clever trick. You can insert, so let me put the arrow this way. So we extract from the event a uniform density of contamination rho. And then we can insert a uniform spray of so-called ghost particles of density minus rho into the event. So if you can estimate what the contamination is via some technique, and you can just insert a uniform spray to counteract it, then you can just calculate all the jet observables that you want to calculate, and you will have eliminated on an event-by-event basis at least uniform contamination. You could try to be more sophisticated and bin it up in different values of the rapidity. But it's a very cute method, and this method of using ghost particles as a way of showing where the contamination can end up is a really elegant way of correcting this contamination problem, and you can apply this to all the substructure observables that I talked about today. So it deals with event-by-event fluctuations of pileup. On each event, I'm going to have low, high pileup. This one has 20 primary vertices, this one has 50 primary vertices, and this technique can correct for that. So this is a zeroth order correction. Well, sorry, the zeroth order correction is you just do an overall shift. I guess I would call this the first order correction. First order is you deal with event-by-event fluctuations. You deal with the fact that some events have more pileup than others. So this is the first example of a kind of jet grooming method in that you just actively cancel off the contamination by introducing your uniform spray. This works for pileup, doesn't work as well for underlying event or ISR because those don't fluctuate on an event-by-event basis in the same way as pileup does. So the next thing you'd like to do is you'd like to go to second order. And you want to deal with fluctuations within an event. That is, you want to deal with the fact that maybe there's more pileup here versus inside the jet, or one jet has more pileup compared to another one. And there, it's a little bit more complicated about how you do things, and I would say it's an evolving field for deciding what the best way to deal with fluctuations within an event would be. But kind of when people talk about jet grooming, what they're really talking about is more of this second order effect. So what jet grooming aims to do, it aims to do active removal of contaminating radiation. So this is the goal in the general strategy here. Our goal is to actively remove contaminating radiation. But now we need to figure out what physics can tell us whether contaminating radiation is contaminating or not. The proxy that one can use for contaminating radiation is one can say, oh, contaminating radiation is generically soft wide-angle radiation. So if you can remove soft wide-angle radiation, soft stuff not really collimated with the jet that you're studying, that's more likely to be contamination from pileup, more likely to be contamination from initial state radiation and underlying event. It's not a perfect strategy, but that's the strategy we've come up so far. And removing soft wide-angle radiation is what jet grooming techniques do. And the hard part is deciding what is soft. If I have some jet, let's say it's a boosted top jet with my radiation here, and I have some contamination, let's say one extra pion added to my event from pileup, this guy is going to distort the mass by some amount, and generically you expect it to be soft, and so you want to test for removing the soft particle. And the first thing you might say is, oh, I just want to remove all pions whose energy is below some threshold. And one could try to do that. Indeed, when you have noise in your calorimeter, you essentially do a type of noise suppression. And if you apply that to individual particles, it would be like noise suppression on an individual particle, and that's perhaps okay. But one of the challenges is that if you try to apply this to individual pions, you're very sensitive to hadronization, non-perturbative effects. And so all the hard work that you tried to do to stay in the land of perturbative QCD is thrown out if you test softness on a particle-by-particle level. You don't want to test softness on the parton level. So you don't want to test softness on the hadron level. You would prefer to test softness on the parton level. So we'd like to test on the parton level. And what these jet grooming techniques are doing is they're coming up with tests on the parton level that can test for softness in a way that's consistent with the infrared and collinear structure of QCD. And so let me just tell you one example which I can say very quickly, which is the technique of jet trimming. So again, just one example of many examples in the literature. This one just happens to be easy to state. So what jet trimming says is it says, okay, I want to do a test for softness, and I want to take an original jet. My original 4-vector of my jet is built up over all the particles within my jet of the 4 vectors of the individual particles. So this is the regular jet. And now I want to form a trimmed jet by taking all the individual particles and applying a weight to them. And what this weight is going to be is it's going to be 0 if it's soft, whatever soft means, and 1 if it's hard. And in some sense, all jet grooming methods are of this form. You say, do I keep it or do I not keep it? You can even imagine making this a continuous weight if you wanted to make your life more complicated. But I want to say, okay, 0 if it's soft, 1 if it's hard. And the original jet grooming techniques were based on using recursive clustering algorithms, which is maybe a little bit hard to visualize. But here, let me just give you a version of jet trimming, which is not published anywhere, but a version of jet trimming that you can just see what the answer is and see what jet trimming is doing. And just by giving you a specific weight that accomplishes removing of soft, so that I can stay in analytic land and not have to talk about jet algorithms. So we're going to have a theta function. Theta function is 1 if this thing is positive, 0 if this thing is negative. And so I want to have a theta function that tests whether something is hard enough. Do I get larger than some z cut, that is some fraction of the energy? Is this thing hard relative to something? So is there a high enough energy fraction? If so, then I keep it. If not, then I throw it out. And what is the test that you want to do? Well, it's the most basic test you could think about. You want to say, well, compared to the PT of the jet, is an individual particle hard compared to the PT of a jet? Now, I just told you I can't talk about individual particles, so I need to think about something more clever. But what I can do is I can say I have my overall jet. My overall jet has some PT. I'm testing for an individual particle whether to keep it. But I want to do this not at the hadron level. I want to do it at the parton level. So let me just make a little circle around my particle and ask whether in this circle, do I have enough radiation in order to qualify as being hard enough? And this thing, because I'm integrating over many particles, I'm consistent with the soft collinear singularities of QCD. I'm allowed to do this, and I just need to find a formula for that. Well, what is it? It's just saying I take all my particles in my jet, I sum up their PTs for those particles, but I only contain them if their distance to the particle in question is less than some small size r sub. So I have a big jet radius r. I have a small jet radius r sub. I have a fraction of how hard does hard mean. And now I have a formula that tells me how to generically groom a jet observable. And there's some really nice studies from Atlas showing that if you appropriately choose the subjet radius and this energy cut, you can actually get a situation where jet observables are basically independent of the number of pileup events. That basically between 0 and 50 pileup events, the observable you get is extremely insensitive. Why? Well, because pileup tends to be soft. And if you just have some sort of cluster of radiation coming from pileup, it's unlikely to cross the z-cut criteria. And until you get to, let's say, 100, 150, 200 pileup events, only then do you start running into trouble where you can have enough pileup concentrated in some area where you could fake hardness by overlapping a bunch of soft things together. Okay, so with that, let me conclude with just a statement about the future of jet substructure. So what I've told you about in these 2 lectures is I've told you kind of what jet substructure is and given you 3 case studies. I've talked about quark versus gluon discrimination, essentially one-prong discrimination. I've talked about multi-prong discrimination, boosted WZ Higgs top. And then I've talked a little bit about jet grooming, where you're trying to deal with the anticipated problems that pileup are going to pose as we go to higher luminosity. And as I said at the beginning of my first lecture, the excitement in jet substructure is that there's developments happening in both experimental land QCD theory land and beyond the standard model theory land. And let me just say in words, and these are given in my handwritten notes, things that I think are going to be happening at the boundaries of these areas and the excitement that's going to be happening, especially at the intersection. So experimentally, the theory community has flooded the archive with all sorts of jet substructure methods, and in the near term, the experimental community is going to take up a number of these methods. They've already started to do quark versus gluon discrimination, boosted objects, applying jet grooming to a variety of searches, and they're starting to do really exciting validation in data and starting to see places where there's discrepancies between Monte Carlo and data, and those are giving us hints as to what's really going on in these Monte Carlo programs in ways that we in theory land can improve things. The longer term thing that experiment's going to need to deal with is how to deal with jets in a high pileup environment, and can we continue to do standard jet triggering, standard jet analysis in a high pileup environment, or are we going to have to start doing these jet grooming methods all the time? Is that going to have to become incorporated more into the data analysis scheme in experiment? So that's something that's kind of long-term that the experimental community is going to have to think about. In the QCD theory community, we've had the success of understanding one-prong objects, quark versus gluons. We have had comparatively less success, though there was a recent nice paper on the archive about applying some of these grooming methods and seeing how they perform analytically. But some of these two-prong or three-prong tagging methods, we just don't have the analytic tools at the moment, and we hope to develop them. Hopefully, we'll be able to use those analytic calculations to understand where you might have problems with Monte Carlo, places where QCD theory needs to push harder. In the long term, the QCD theory community is going to have to deal with non-perturbative effects. Everything I've talked about in these lectures has been perturbative, 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 but non-perturbative effects can matter, and whether those impact jet substructure is something that we need to understand. And finally, in the BSM theory community, basically, if you have a model and you want to test it, you kind of don't have an excuse anymore. If you have boosted topologies, you should probably be using boosted techniques. And don't say that your model's not discoverable if you're at some very high mass object giving you collimated top quarks. In fact, that's the perfect place to be using jet substructure. There's a more global question, which is whether we should be talking about jet substructure or whether we should be talking about jet substructure and jet superstructure all at the same time. If you really think your beyond the standard model process gives you some 10-jet final state, that's some interesting combination of jet substructure, jet superstructure, and the BSM and QCD theory communities need to talk a little bit more about that issue. And in the long term, what model builders are very good at is finding blind spots. And is there some jet analysis that we're just not sensitive to with existing techniques? With high luminosity, is there something that can be buried where jet substructure could dig it out? And similarly, are there other opportunities in the boosted regime? We already mentioned new physics objects getting boosted. Is there more that we can do with that? It's been a lot of fun telling you about this exciting developments in jet substructure and looking forward to more questions from you right now and also this evening. Thank you.